Okay. So the task we have already seen multiple times. What we are given is this n data points in a d-dimensional space, and our task is to find d orthonormal vectors so that they eventually become a basis, an orthonormal basis for this d-dimensional space. But we want a very special kind of basis, v1, v2, vd. What is that special requirement we have? You take any k, then the first k of these basis vectors, you take their span, that should be the best k dimensional subspace for your data. Okay, that's the requirement that we were having all the while along. Okay, instead of writing it one bullet point after the other, I just have said for every k in this range 1 to d, the first k of your singular vectors should span the best k dimensional subspace for your data. And we finally formulated everything in terms of a matrix multiplication. The matrix A that we were talking about, recall, was just each row of the matrix A was one data point. Okay, so this was that n by d matrix that we had. Okay, and we already saw how to find the first singular vector in this context. Okay, it turns out to be like our search space is all unit vectors. Okay, so this is our search space, right? This will be in 3 dimension, this will be all the vectors on the surface of the unit sphere. Okay, that's nothing but all the unit vectors, right? All the vectors which are on the surface of the sphere. If your ambient space d was 2, then this is all vectors on the unit circle. In higher dimensions also there is a equivalent, even though actually it really gets interesting what is a unit ball in the higher dimension and so. Okay, and what was our solution for v1? We formulated it in a way such that the proof also was immediate. The v1, the best or the top singular vector, turned out to be the vector that maximizes argmax among all the vectors on the surface of the sphere, the vector that maximizes the norm of AV. Okay, A times V. This was our top singular vector. Maybe I wrote AU last time, but that's okay. Okay, now the general case is about how to find v2, v3, v4 and so on, okay, up till vd in a d-dimensional space. So here I will state what is the algorithm typically used first, and in the next 10 or 15 minutes I will see why it is so. At least we will see why v2 is so. Okay, we may not do the general case, but we will do at least why v2 is so. Okay, so what is the second most important singular vector? Okay, the v1 is the top singular vector. Now focus on v2. Okay, the algorithm looks like exactly the sentence above, exactly the formula above. It's again argmax over V running over the surface of the sphere, V element of this capital V, which is nothing but surface of the sphere. Again, what you are optimizing also looks the same, which is the norm of AV. The only additional thing here is this condition, that now we are only looking, our candidates, our search space has reduced. We are now looking not for every possible vector on the unit sphere, but we are only looking among those vectors which are orthogonal to the first vector we already found. Okay, so this is an iterative algorithm. You can find v2 only after you have already found v1. Okay, our search space is limited to those which are orthogonal to v1. Okay, so suppose our d was 3, again just to see that we are all visualizing in the the correct way. If our dimension was 3, then the search space for v is the set of vectors on the surface of a unit sphere. Suppose your v1 was the the vector along the z axis, let's say the north pole of the equator. What is the search space for v2 now? Huh? Yeah, I think you are correct. It's x and y, but what the search space originally was the surface of the sphere. You could pick any vector from the surface of the sphere as your v. But now you have an additional restriction. It's still on the surface of sphere, that's what the first condition says. But among that, you have another restriction. The second restriction is that it has to be orthogonal to the first vector. So what do you get? Huh? Sorry? Yeah, but it's not just two choices. It's not east or west.
Or anything in that plane.
Exactly. It is anything in that plane, or rather it is in that slice that the xy plane will make with the sphere, which is nothing but the equator. Okay. So your search for v2 is now limited to a circle. It's limited to the boundary of a circle, which is in this. If the V1 was the equator, then the circle would be the if V1 was the north pole, then the circle would be that of the equator. If V1 was at some angle, it would be that circle in the sphere which is perpendicular to the north pole. You take to V1, okay, V1 to perpendicular to V1, you get a plane. That plane will slice the sphere and give you a ring or a circle. That circle is where it is the search space for V1. Let's imagine like when it goes to V3, it's not much of a use imagining it in 3D, because once you fix two orthogonal vectors in a three-dimensional space, the third one is automatic, because the first two vectors will span a plane, and if the third one has to be perpendicular both to V1 and V2, it essentially has only two choices, okay, because the V1 and V2 already defines a plane. Your third vector V3 has to be perpendicular to V1 and V2, which means it has to be perpendicular to this plane. That leaves only two choices, right? The one and the diametrically opposite one to that. Okay. So in 3 dimensions, V3 search for V3 is simple. It's about only these two vectors, and they don't actually matter, because you are always taking the norm and maximizing it. So whether it is V3 or minus V3, it doesn't matter. So in order to see the non-triviality in the search for V3, the ambient space should at least be 4-dimensional. So your V1 is a search on the surface of a 4-dimensional sphere. Your V2 will be something which is very interesting. You take V1 in a 4-dimensional space. What is perpendicular to V1? If your ambient space is 4-dimensional, what is perpendicular to V1 is a 3-dimensional space. And when a 3-dimensional space, subspace slices a 4-dimensional sphere, you get a 3-dimensional sphere. And this 3-dimensional sphere over is your search for V2. Once V1 and V2 are fixed, you get a plane, and if you slice a 4-dimensional sphere using a plane, you are left with again a circle. Your search for V3 will be in the circle. Search for V4 will be trivial. Once you fix all the d-1 dimensional d-1 vectors in your decomposition, the last one is almost automatic. Okay, so this is what this algorithm is doing. Okay, you are iteratively finding the best singular vector, the next best, the next to next best, and so on. Okay, but this is not exactly how we defined the best fit subspaces, right? There is a difference here, and that the difference is subtle, but it is something I want to highlight. Let us come back to a picture that we can all visualize. Think about the 2D subspace in a 3D ambient space. Okay. So think about the Milky Way trying to center, the origin being at the Sagittarius A, that massive black hole in the center. We want to find the best fit plane 2-dimensional subspace for the data. The picture so far was, okay, you take a plane through the origin, but then you kind of tilt it, rotate it, do whatever wiggling you can do. Center should still be in the plane, and among all these planes you calculate the projection and the total projection and find out which is the best. That was the picture we had in mind. But now suddenly we are saying we can do it in 2 steps. You don't need to carry this whole plane like a magic carpet, Aladdin's carpet, and kind of swirl it along. You first find the best line, okay, and next you look at all the lines that are perpendicular to the first line. So the first line will leave a plane that is perpendicular to it. So you are saying, instead of doing the optimization over all possible wiggling of the plane, you can do it in 2 stages. First find the best line, and then find the second line is the best line among those which are orthogonal to the first line. Okay. So this is not obvious, right? That this way of attacking the problem one vector at a time is equivalent to actually finding the best 2-dimensional subspaces. And this question continues when you have d dimensions. You have is finding the best 3-dimensional space by taking a 3-dimensional space and wiggling it around and finding the best space. Is it same as first finding the best vector, then finding the best vector which is among those which are orthogonal to the first, and then finding a third which is orthogonal to the first 2. Okay. So this requires a proof. The proof also gives you a lot of understanding of what is happening. So we will do the proof after I mention a bit more about this algorithm. Okay. the way I have written this, it doesn't like kind of look like an algorithm. There is not even a loop there. So usually you write it as a for loop. Okay, for I from 1 to d, what is vi? Forget about the sigma I and ui for now. Look at only the first line inside the for loop. Okay, how do you find vi? It is argmax over av, where v runs over a search space. What is a search space for v? First of all, it is a unit vector. That's what the first two lines will say. It's a d-dimensional vector with length 1. So it's on the surface of the sphere. What does the second condition say? It is perpendicular to all the vectors that we have already found. So when I is equal to 1, the second is no restriction at all. It says your v has to be orthogonal to an empty set, which anyway every vector is. So no condition at all. When I equal to 2, it says your v has to be perpendicular to v1 that was found in the previous iteration. Third iteration, v has to be perpendicular to both v1 and v2 and so on. Okay. So if you put the previous slide in a loop, if you put this previous slide in a loop, this is what you get. Okay. But whenever you have an algorithm, you squeeze a bit more out of it. You just don't stop at getting v1, v2 up to vd. You get something extra. Okay. So far I was saying, it's only the argument of the maximum that is important. Okay, which is that maximum value is not so much of an important, but there might be cases where we are interested in that maximum value also, in which case anyway while finding the finding the argmax, you will also end up getting the max. So that is being stored in these real numbers sigma 1, sigma 2, etc., all the way up to sigma d. Okay, this is that maximum value. Okay, and this values are called singular values. Okay, the first vectors are called singular vectors. These values are called singular values. Okay, this will all be, in fact, since it's a norm, it will be a positive, it will be a non-negative real numbers. Okay, remember v1, v2, etc. are d-dimensional vectors. There are d-dimensional vectors, but these are d real numbers. Sigma 1 is a real number. It's called the top singular value. Sigma 2 is called the next best singular value, and so on. In some sense, it kind of quantifies your image. If you think about the Milky Way and you take sigma 1 and sigma 2, sigma 1 square plus sigma 2 square will kind of tell you how much of your information you have already captured in the two-dimensional approximation. So it's v1, v2 gives you the best 2D approximation. Sigma 1, sigma 2 kind of has the information as to how good is that best approximation. The third thing, which is even slightly more rare, is to also store the result of AVI. Okay. Now, your v1, v2, v3 are vectors, so matrix times vector will give you another vector. In fact, these results are going to be vector of n. It's not d-dimensional vectors; these are going to be n-dimensional vectors, right? If you recall this slide. Okay, no, that slide has gone. Okay, AVI, whatever that vector is, you normalize it. The normalizing is the 1 by sigma I part, okay, because the norm is already sigma I. In order to get a unit length vector, you just have to divide it by sigma I. These are called UI. So typically any implemented SVD algorithm, by the way, every programming language like Python, MATLAB, almost every programming language has a library which will give you SVD. It will not just give you the singular vectors v1 to vd, it will give you all these three groups of things. It will give you v1 to vd, which are known as singular vectors, or to be precise, right singular vectors. It will give you u1 to ud, which are the left singular vectors, and sigma 1 to sigma d, which are the singular values. Okay, so it comes as a package. If you run an SVD command, you will get all these three together. Okay, and as I told you, this is a greedy algorithm because you first find v1, and then among what is left out by v1, among what v1 doesn't span, you look for v2. Then after you find v1 and v2, among what is left over, which is some things which are neither spanned by v1 or v2, orthogonal to v1 and v2, you look for v3. And I'm essentially taking this lecture mostly following this book by Blum, Hopcroft and Kannan. Ravi Kannan, at least in his lecture, also says that this is probably the earliest greedy algorithm, not our Kruskal or Prim or anything. This is much earlier than that. As I told you, SVDs is like known from 1873 onwards. So this procedure to calculate this is known from very long. Okay, but this exact proof of correctness is only around like 1936 by Eckhart and Young. Okay, and yeah, the actual thing inside the loop is to be solved using a quadratic program. Okay, so this is the algorithm. and we now we will spend time on the proof of correctness part, at least why the second vector is this. Okay. So what are we, another way to, again it's not a very important slide, but what I want to say is that when you look at literature in SVD, you may see SVD just defined using this algorithm. Okay. It may sound strange in the beginning, but you can really define a thing using an algorithm. You can give an algorithm like this and then claim that whatever this algorithm, the V1 to VD, this algorithm outputs are the singular vectors of the data. Okay. In fact, many people actually do that, not the majority, but at least a significant amount of people do that. And then you think, there are two conflicting or alternate definitions for SVD. One is what we have been talking about a lot, like it's a sequence of vectors V1 to VD such that for the first k of them span the best k dimensional subspace for the data. And the second alternate definition is that you give this algorithm and say that whatever this algorithm returns is the SVD. Okay. And our task is to show that it's okay, both definitions actually give you the same thing. Okay. Yeah. So let me skip this part. I wanted to reach till there before the break. Okay. So I need a small digression, like 5 minutes we will go back to our projections. Okay. We already spent some time with the visual image of what a projection is, starting with projecting a 3D vector onto a 2D plane. If the target two-dimensional space was horizontal, then it is like dropping a weight, but it could be inclined, in which case it's not dropping a weight, you have to really drop the perpendicular to this plane and so on. And we wrote a formula for this projection, at least when the target space was one dimensional, as the inner product of the x with the unit vector in the direction of the plane, right? That is what we use to essentially arrive at the SVD algorithm or write the optimization as a matrix vector multiplication. Okay. So now look at the left part of the slide. Suppose now S is a general k dimensional space. Again, let's imagine a two dimensional space, an inclined space. You have you are given an orthonormal basis for this space. Okay. So this is your origin, and okay, this is not necessarily the horizontal plane. This is some two-dimensional space S, and you are given a orthonormal basis vectors V1 and V2. V1 and V2 are perpendicular to each other, both are of length 1. That's what an orthonormal basis means. Okay. Now let's say I have another vector somewhere not in this plane, X. Okay, and I drop a perpendicular to this. Okay, and this is what I mean by X's projection on S. Okay, if S was one dimensional, we knew how to write a formula for this projection, but if S is two dimensional, what would be a corresponding formula? If you know both B1 and B2, inner product of, so X projected to S is equal to what? Okay, this you would have called it, it's like resolution or whatever. No? So what would be X's projection on the line along B1? Do you remember? Yeah, that will be inner product of X with B1 into B1. Okay, B1 arrow. B1 is already a vector. I said I won't denote vectors with an over arrow or an over bar. Okay, what about along B2? What is X's projection along B2? Okay, and this sum turns out to be the projection of X along the plane. Okay, you can resolve it in this way. So this is how you will quantify. So now if I have to look at what is the length of X of S squared, that turns out to be X B1 square plus inner product x b2 square. Okay, remember we are interested in the length squared of the projections. In fact, this only works if b1 and b2 are orthogonal. Okay, if b1 and b2 were at a angle different from 90, you will have to do a bit more work to find out what is the orthogonal projection. Okay. If you want to prove it, you can actually prove it by doing a second projection to x projected on S. Okay. Think about what would be x projected x on S when it takes a second projection onto B1. Similarly, you do the other way, but okay, let's not digress too much. Okay, we probably will then spend this here. Okay, so this is the okay, so this that I'm trying to express this in a slightly different format. Okay, this is maybe I should right. Okay, I'm trying to get at this point, but let me go back to the picture and try to get at that point. Okay, so this vector here. Okay, let us analyze. Okay, we have an x times b1. Okay, so in x inner product b1. So I have all two ways to write it. I can write it as x transpose b1 or b1 transpose x. Okay, we are in real numbers, so it doesn't matter. So maybe I will write it as b1 transpose x this time, right? So this orange part, I can write it as b1 as a row vector times x written as a column vector. Okay, the b2, the second, the blue part is again your b2, right, written as a column vector, right. So if I take these two b1 b2 as rows of a matrix and I take x as a column vector, what I get are the two coefficients. Okay, b1 inner product x or x inner product b1 and b2 inner product x. Okay, so I have got a column vector which contains these two scaling factors, right? But now that is not enough for me. I need to add this b1 and this b2 here. Any idea? Can you represent that using a matrix multiplication? B1 0 row b1 b2, no. Okay, so for example, if I have some two scalars a and b, and can I represent, or let's say alpha and beta, can I represent some alpha times some vector v plus beta times some vector w as a matrix operation? No, because we need v and w to come somewhere. Okay, what I can do is I can yeah, so this is alpha times v1 plus beta times w. In fact, that is one interpretation of a matrix column vector multiplication. Yeah, correct. So if I write a matrix like this, okay, in fact, you know, this matrix, I usually when I teach SVD as part of a larger course, I spend one lecture only saying the 4 different views to view a matrix multiplication. Okay, there are multiple ways in which you can view matrix multiplication. One is like when you are multiplying a matrix with a column vector, you can think of the answer to be generated term by term, which is what we have here. Okay, I am taking a row of the matrix, taking inner product with the next column vector, that gives me the first entry in the answer. Second row inner product with the column gives me the second entry in the answer. This is very useful way, this is one, but this is only one way. There is another way, which is don't look at your matrix row by row, look at the matrix column by column, then you will get the answer in one shot, at least in your mind. I'm not talking about the calculation part. The picture that comes to your mind will be one shot. The result is going to be a linear combination of these columns, and this x vector that you are going to multiply is going to be the coefficients of the linear combination, and the vectors are going to be the column vectors of this matrix. Okay, that's the picture I am talking about here. Okay, so in general, if you have a matrix A, you express it as column vectors A1, A2, etc., some AN, and you have some x here, which is x1, x2, xn. The result will be x1 times a1 plus x2 times a2 plus etc. xn times an. Okay, so it's just a matrix column multiplication is a linear combination of the columns of the vector. It's one view. The alternate view is, instead of viewing the matrix like this, you view it as some b1, b2, some bk rows of it, right? And then this will be again your x1 to xn, or you can just write it as x even, and then you will get entry by entry. It will be b1 inner product x, b2 inner product x, and so on, bk inner product of x. Okay, so this is the second. There are two views in which you can see matrix multiplication. We have already used the second view, but now that only gave me the coefficients, but I now have these. I have to take these coefficients and put it as linear combinations behind b1 and b2. So the way to do that is now to pre-multiply this with another matrix where I put b1 as a column like this and b2 as the second column like this. Okay, then I will not get just this. This will be the intermediate part, right? This will, but it okay. What I will actually get is the first part will look like b1 x, b2 x, but now I am pre-multiplying it with b1, b2, which I will get as this inner product, no? b1 x times b1 plus b2 x times b2, which is exactly what I want. Okay, so finally, instead of doing this multiplication this way, I can think of taking this as a single matrix. Okay, so if this is the B matrix, usually you represent vectors as columns, right? So if B is the matrix which contains the orthonormal basis as the columns, then what is this? This is B transpose, right? So this whole matrix here is B transpose. Okay, so taking projection of a vector x turns out to be multiplying that vector with B transpose. If each column of B, for the columns of B form an orthonormal basis for the target subspace. Okay, this is a very useful thing even outside SVD. Okay, this is extremely useful in SVD, but this view of projection as a matrix multiplication is how projection is actually implemented. Okay. In fact, any linear transformation you can represent with a matrix multiplication. There is no surprise there. The surprise here is about which particular linear transformation represents projection, this orthogonal projection. Okay. So, yeah, so that's what I have written here. The projection of x on S in general can be written as B transpose x. Okay, where the columns of B form an orthonormal basis for the space to which you are projecting. Okay, and this reason what I have written here I have explained in detail already. Is this clear? We are not going to use it exactly now, but it should be clear that projection is a very well codified operation. You can just represent it using a matrix multiplication. B transpose is called the projection operator. Okay. So let us say, okay, let's skip that. Move ahead. Okay. Now we are ready to see the proof of that claim. Okay, we will prove it in the case of till the second singular vector. Okay, we said first singular vector was the best line that fits the data, and essentially we only kind of did some formulas to represent it as optimizing some AV where V runs over all unit vectors. But then the second we had this conflicting definitions, right? One said you have to take a plane through the origin, wiggle it and find the best plane. The second said you can actually do it one step at a time. find the first singular vector and then find a second vector which is the best among guys orthogonal to it. The question is, why is the second one as good as the first? Is it clear that the first is supposedly the best? Because that gives you all the options, including what the algorithm has. Algorithm is taking the first vector and then the second vector. The mental picture of wiggling the plane is free to take this also as one candidate plane. So that is surely not going to be worse than taking one vector at a time. Your greedy algorithm is never going, or the greedy algorithm is kind of competing against an arbitrary optimum algorithm. Okay. So what we have to show is that doing it one step at a time still produces the best combined effect. Okay. And in the class we will, in this today we will just see why it works till the step 2. And actually generalization to arbitrary steps is by induction. You just have to use the same idea. We go through injection. Okay. So let me set up some notation. Okay. So for ease of imagination, think that the ambient space is 3D and we are looking for the best 2D subspace. Okay. So that best 2D subspace is what I denote by S2, right? That is pictured in this. This is not necessarily the one given by the SVD algorithm. This is the one that you get if you take a plane in your hand and wiggle it and find out the best plane. Okay. So that is S2. V1 and V2 are the top singular and the second top singular vectors returned by the algorithm. Okay. We have to prove that V1 and V2 are as good as the best, as good as S2 in terms of maximizing the projection, sum of projections length squares. That's the target. Okay. Don't get scared. Again, there are details, but more than the details, I'll tell you what is the key idea in the proof, and the rest it should be the details. Okay. So is the notations clear? What is S2 and what is V1 and V2? Most importantly, S2 is as of now not the span of V1 and V2. V1 and V2 might span something else which I denote by S2V. Okay. The span of V1 and V2 is S2V. That might be a plane which is slightly tilted away from S2. Okay. So we are considering two planes at the same time. SV is the unconditional best. S2 is the one given, S2V is the one given by a greedy algorithm. Okay. Okay. And this should have been, suppose if they were the same, we have nothing to prove. Okay. Then anyway the SVD gave you V1 and V2, its span was S2 itself. So V1 and V2 form an orthonormal basis for the best 2D subspace. The question is, what if these two subspaces S2 and S2V were different? Okay. Now here is, but by the way, okay, before going into the proof, how many of you think a proof is unnecessary here? Okay, or maybe how many of you think a proof is necessary here? Yeah, you see there is a gap, right? Taking the 2D plane and wiggling it in all possible ways and finding the best is a much more complicated procedure, and our best is actually defined on that complicated procedure, whereas now we are saying a much more simple procedure, a greedy procedure which finds one vector at a time is equal to that. Okay. So you need a proof to show that going one vector at a time is equal to that. Okay. So I hope it's clear what we are trying to prove. Okay, no proof will make sense unless you realize the need for that. Okay, that's a problem with proving many things. Like you would have experienced the same thing with many first algorithms in data structures, right? Prims, Kruskal, etc. Feel so obvious that you will wonder why somebody proves its correctness. This is so. Yeah, I hope you have got what is the need for the proof. Okay, so now for S2V we already have an orthonormal basis V1 and V2. We are going to now construct an orthonormal basis for S2, the best plane that you get. Okay. Remember, once it's a 2D plane, the orthonormal basis is not unique. Once I get an orthonormal basis, I can rotate it, it still remains an orthonormal basis. So we are looking to find a particular orthonormal basis which will help us complete the proof. Okay. And this is how we are going to pick the orthonormal basis. Okay. We are going to find a W1 and W2. Interestingly, we will find W2 first. Okay, we are really crazy. We are not finding W1 first. So W2, since it has to span S2, surely is going to be a vector from S2. That is clear. Okay, our W2 is going to be from S2, okay, somewhere in this S2. The most important part is that we are going to insist that W2 is perpendicular to V1. Okay, so if this is V1, your W2 is going to be perpendicular to this V1, so it's going to be something like this. Okay. Question: are we sure such a W2? Sorry, are we sure such a W2 exists? Will we find something which is at the same time in S2 as well as perpendicular to V1? This is 3D picture, so you can tell me the answer in terms of planes and their intersections and so on. Not sure, right? Huh. Any altering answer, any differing opinion? Okay, so let me try to, then actually the answer is yes. Okay, let me try to say why. So condition 1 says W2 has to be in S2. So can you imagine S2 as some inclined plane passing through the origin in an ambient 3D space? Okay. Condition 2 tells you that W2 has to be orthogonal to V1. Now, what is the collection of vectors orthogonal to V1? The plane that is normal to V1. Okay. So if you have to satisfy both these requirements, your W2 has to be in the intersection of these two planes. But these are both planes passing through the origin. So if you intersect two planes, both of which are passing through the origin, what is the answer? What is their intersection? It is a line. Any two planes, unless they are parallel, they will intersect in a line, or maybe if they are, unless they are the same, they will give you the everything. If they are parallel and not the same, it will be empty. But here anyway, they cannot be parallel apart because they both contain 0. So there is some intersection, which means it will intersect in a line. Okay. Only other cases when they are the same plane, but that we have anyway discounted. We are anyway assuming that S2 is not equal to S2V. So the intersection is a line through the origin. That's a one-dimensional subspace. So your W2 you can pick from there. Okay, is that clear? So W2 exists. That is your W2. Okay, it is in the intersection of these two planes. First plane being S2 and the second plane being the one orthogonal to V1. Okay, I shouldn't have said they cannot be the same because S2V is equal to S2. The S2V still haven't played a role here because it's orthogonal. The plane that we are talking about is in fact orthogonal to V1. So it's just two planes, their intersection either would be a line or more. If it's a whole plane, then you have abundant amount of choice for W2, that's all. So and anyway we have all the vectors in this line to pick from, we will pick a unit length vector. That is your W. So third condition is easy to meet. Combinedly meeting these two conditions is where we require the geometric argument. Okay, so that is W2. Now, how do you pick W1? Again, we are looking to construct a basis for S2. So W1 also has to come from S2, and we will pick it to be orthogonal to W2. This is even more straightforward, right? You have a 2D plane, you only have a restriction that you have picked one vector, now you have to pick the second one. Okay, so this is W2. Okay, so now that we have a basis for S2 also, which is W1 comma W2. W2 is also, by the way, unit length, so this is an orthonormal basis. W1, W2 is an orthonormal basis for S2. For the S2V, we already had an orthonormal basis, V1 and V2. So now we can compare the projection on S2 and the projection on S2V. That will complete the proof. Okay, we will show that the projection on this S2V is as good as the projection on S2 itself, and hence our greedy algorithm is good enough. Okay. Okay, so recall that what are we searching for? We are searching for that S which maximizes the length of projection squares. Okay, now let us analyze this length of projection square for S2, for S2V on the red side and for S2 on the green side. Okay, let's do the S2V first. Remember, what would be the projection of any arbitrary vector x onto S2V? S2V has this orthonormal basis V1 comma V2. So this will be the projection to S2, okay, inner product with the orthonormal basis along the direction of the basis itself, okay, and its length square will be just square of these inner products summed together, okay, and this is about one vector x, but we sum this quantity over all the vectors in your data set. That is what the summation is doing, right? The summation, when you do it over all the vectors in your, that's the quantity we are, the summation, this quantity, this whole summation is the quantity we are trying to maximize. So, which is exactly this when it comes to here. So, we already saw that inner product square can be written as like AV1 norm squared. I am kind of using what we did for the case with the top singular vector here. Inner product with V2 square, you can write it as AV2 norm square, okay. AV2 will give this x1 V2, x2 V2, x3 V2 inner products in a column. Squaring and adding them is equivalent to taking the Euclidean norm square. Okay, since we already did it, I am kind of not going back. Now, the same analysis we do on the green side, this time with S2 and W1, W2 as the orthonormal basis. Same calculation, you will finally get the sum of projection length squares as AW1 norm squared plus AW2 norm squared. Okay, it's the same analysis. Once we did for V1 and V2 orthonormal basis, green side is for W1 and W2 orthonormal basis. Okay, now is the final icing of the proof. Okay, I have to claim that the red side is at least as good as the green side, because green side is for S2, the best plane you got by taking the whole plane and wiggling it around and finding it. Red side is about the singular vectors, which is the greedy algorithm. So, and we are maximizing. So, I have to show that if the greedy algorithm, to argue that the greedy algorithm is correct, I have to show that the red side is as good as or at least as large as the green side. Okay. So, we will kind of, it is like a match between a two-player team on one side and a two-player team on the other side. Okay. So, we will kind of pair them up so that in both cases the member from the red team will win. Okay. So, who can I beat AW1 norm squared with? Okay. Our AV1 norm squared, I claim, will be as good or even better as AW1 square. Can you say why? Okay. I am asking about this line. Why is this line true? How was V1 chosen? What did you maximize to pick V1? Yeah. Okay, I'm going to. Okay. Yeah. So what was V1? Or maybe even the previous slide, I'll have it just V1, right? Yeah. What did we maximize to find V1? V1 was that vector which maximized norm AV or norm AV square equivalently. Because nobody can beat V1 in that aspect, because that maximized AV1. So, in particular, when you come here, AV1 square is better than A whatever norm square. In particular, it is better or equal to at least AW1 square. So, V1 handsomely beats W1, because V1 is chosen by an optimization which picks the quantity that maximizes norm AW1. But V2, remember, now we are getting into trouble. Okay, V2 was a very restricted maximization. V2 was only allowed to be a vector that was orthogonal to V1. Among those, the best one was V2. Remember, right? Right, what was V2? Among all the vectors that are perpendicular to V1, among all the unit vectors orthogonal to V1, we found out V2 to be the one that maximizes AV. So, this restriction was there. So, V2 is not a unconstrained best guy, right? It is the best guy among those which are perpendicular to V1. Okay. Now, but even with this handicap, even with this restriction, I claim that V2 will beat W2. Why? Because W2 is also perpendicular to V1. So W2 was also in the search space. W2 has the same handicap, right? So among them, among those which were orthogonal to V1, V2 was the best. W2 is also among them. Hence, it beats that. Okay. This is why we could have chosen many different orthonormal bases for S2 to complete this proof, but we chose it in a very smart fashion like this. We first chose W2 to be perpendicular to V1 and then went back and picked W1. If you started with a W1, this proof wouldn't have worked. Okay. Now, it's okay if you did not completely follow this proof, but in my opinion, it's kind of a very subtlety. Otherwise, you may think this algorithm is kind of obvious, but this is a non-trivial greedy algorithm, and a greedy algorithm which really is optimal because of all this proof that we just argued. Okay. Extending it to larger dimensions is by induction. You assume that the subspace you have found so far is the best, and then you put one more vector. The property of being best is retained, and there, in order to complete the proof, you will pick Wk first and then keep going back and so on. Okay. The idea is this, but you have to do a proof carefully using induction. Any questions? Okay. So now we are, I mean, if you even did not follow the details of this proof, it's okay. We are taking a slightly different direction now. Okay. So far, we only talked about, singular vectors, and in one slide I kind of told what are singular values, what are right singular vector, left singular vectors, etc. But the title of all this topic is singular value decomposition. So what is this decomposition doing? Okay. So in fact, this is how, as I told you, it's a very historically old area, and hence this was not invented for data science. Singular value decomposition was originally used to study matrix operators, right, or in particular some things called bilinear forms and so on. So all of us know that any linear transformation can be represented as a matrix multiplication, at least in the finite dimensional case, right? You have to choose a basis for the domain vector space, you have to choose a basis for the codomain vector space. Once you do that, you can encode any linear transformation as a matrix. Okay. Now, matrices are just tables of numbers, right? So this actually should surprise you. A table of numbers representing any possible linear transformation. But what is even more surprising is that since this has become so common, people have started viewing any table of numbers as a linear transformation. So the table, our A here is actually just a collection of data points. Each row is just a data point. It doesn't look like it is doing a transformation, It looks like, dead, inanimate data. But suddenly, it might be the case that it's not dead, inanimate data, it is hiding some kind of a transformation. So when you are multiplying this A data matrix A with something like X, you get some X, and you suddenly think of A as doing some action on X, and you get something. Okay, this is the view of matrix as a operator. Matrix as something which transforms one vector into another. Okay, that is the view in which matrix theory is usually more commonly studied, and it is in that context that singular value decomposition is also studied. Okay, so for this slide, or maybe this on the next slide, imagine that A is no more necessarily a data matrix or anything. It could be any linear transformation. Nothing changes. It's just like how you wish to call it. Okay, both are just a rectangular array of numbers, so nothing changes, but view it as something which is doing an operation, right? Now, how are linear what are some examples of linear operations? You can scale vectors, right? Or you can rotate vectors, right? Or you can rotate and then scale and so on, right? One of the beauty of singular value decomposition is that it tells you every linear transformation has the following geometric interpretation. Okay, it is composed of three things. You have one rotation and then some scaling along the XYZ, the standard ordered basis axis, and then you rotate it back. So when you are doing the scaling along the axis, some scale factors may be 0, in which case you will end up with a lower dimensional space and so on. That is fine. That is needed to capture the idea of linear transformation by a rectangular matrix. Okay. So what this is saying is that any linear transformation can be modeled as a chain of 3 operations: rotation, scaling along the basic coordinate axis, and another rotation back. Okay. So it is like you want a linear transformation, you rotate it to some space and then rotate it by something, give it to a scalar and then get it back, do another rotation and get it back. So this says any linear transformation can be decomposed into 3 such operations, and that is where the name decomposition comes from. Okay. So how do we show that this matrix A? Now let us go back to our matrix A. Whether you think of it as an operator or a data matrix, both are fine. Let us see how we can write it as this 3 composition of 3 operators. Okay. So let us start with understanding what is A times V. Okay. Let us start with understanding what is V. Every column of V is the singular vector. In fact, the first column is the top singular vector, right? Yeah. Look at this picture here. This is what is your V. Okay. So it's already written below that it is V. First column is V1, second column is V2. These are not arbitrary vectors. These are the singular vectors. So this form an orthonormal basis and a very special orthonormal basis. Okay. Now this is again a view of matrix multiplication, which if you haven't thought of it before, we talked about matrix column multiplication. But now how do you view matrix multiplication? Here both A is a matrix, capital V is also a matrix. Again you can do it column by column of V, because each column of V is a column vector, so it becomes a matrix column vector multiplication. So the result, this answer matrix also, you think of it column by column. The first column of the resultant matrix, the answer matrix, is going to be A times first column of V. Second column of answer is A times second column of V, and so on. Okay. This is a very useful picture of matrix multiplication to have. You generate the answer column by column, and the ith column of the answer is nothing but A times the ith column of V. By the way, there is a way to generate the answer row by row, but then what you will decompose is not the first matrix, the second matrix, you will decompose the first matrix as a collection of rows, the second matrix you will keep intact, and you can also generate the answer row by row. That is a second view of matrix multiplication. Since we are not using it, let me not digress too much. Okay. Yeah. So with this view, what is the first column of the answer? It is A times V1. But remember, what was A times V1? We called it, the magnitude of that was sigma 1 and the direction was U1. So in total, A times V1 was sigma 1 U1, or in general A times Vi is sigma I Ui. Okay. So this slide I really did not spend so much of a time. When I wrote the algorithm as a loop, I just kind of brushed over it, and I think, yeah, let's not go back. Okay. Or maybe I should. No, when I wrote it an algorithm, this kind of I skipped over very fast, right? So V1, V2, V3 are what we are already familiar with. What is sigma 1? It is a norm of A V1. So think of A V1 as now being represented by sigma 1 and U1. Sigma 1 represents the norm of A V1 and U1 represents the direction, a unit vector along A V1. Okay? Because you have taken the whole vector A V1 and divided it by its norm. So it's just a unit vector. So if you put this together, then sigma I Ui together, just verify the multiplication, will turn out to be just AVI. Okay. AVI is sigma I Ui. Is this clear? Okay. So with that we go back. Okay. So the first column is A times V1, which is sigma 1 U1. Second column would be sigma 1 U2, and so on. The dth column would be sigma D UD. Okay. So now you have this matrix which we understand much more closely. Okay. Now again another matrix algebra trick. Okay. This time let me not try to derive that, but now can you see that this, remember this is not sigma 1 u1 plus sigma 2 u2 etc. It's not a single vector. Okay, this is a dot dot dot, it's not a sum. I am saying each column is this. If it was a sum, then I would have said, okay, now you see a linear combination, I can generate it by taking just u1, u2, u3 as the columns and multiplying it with a column vector called sigma 1, sigma 2, etc. That would have generated that linear combination. But here it is not that linear combination. You still want to keep all these vectors. How do we do that? It's the same idea slightly extended. Your first matrix is still just the columns u1, u2, etc. up to ud. But instead of multiplying it with a column vector containing sigma 1 to sigma d, I multiply it with a diagonal matrix with sigma 1, sigma d as the diagonals and zeros everywhere else. Okay. So if you verify u times, the diagonal matrix will be called sigma, the matrix with u being columns will be called u. Right. So u sigma, if you verify, you will see that you will get back this, right. In fact, how can you verify what is the first entry of the resulting matrix going to be? It is going to be the u matrix times the first column of sigma, which is just the u matrix times sigma 1 0 0 0 0, which will just pick sigma 1 u1. Second column would be the u matrix times the second column of sigma, which will just pick the second column of u, scale it with sigma 2 and put it there. Okay. So, but verify it at your leisure. Okay. Maybe not understanding that is not a serious thing. So, in short, I can write AV as u sigma, where V, A is your data matrix, V has the singular vectors as its columns, the U has the left singular vectors as its columns, sigma is a diagonal entry of singular values, everything should respect the order. Okay. If you are the V1 to Vd are sorted as the top singular value next and so on, all the other guys should follow the same sorting order. Okay. Now you multiply both sides with V transpose, you will get A V V transpose is U sigma V transpose. Again, since V's columns are orthonormal, it's an orthonormal basis, V V transpose will be I. Okay. In fact, V V transpose is the projection matrix onto the whole space. The projection to the whole space is just the identity operator. So recall B transpose was the projection to a space that was spanned by B, if B was an orthonormal basis. In that line, V transpose is also a projection matrix, but a very silly projection matrix, because V is a basis for the entire ambient space, its projection onto itself, which doesn't change anything. That's why that will be the identity operator. So V transpose is identity. This is just a very convoluted way of saying an orthonormal matrix, its inverse is the transpose. Okay. So we finally get that A is equal to U sigma V transpose. This is what is known as the singular value decomposition, and this is the more classical view of SVD. People will say that SVD is about decomposing an matrix operator into three operations: a rotation, a scaling, followed by another rotation. Why is the first one a rotation? That's because V is a orthonormal basis, a linear transformation whose matrix is all columns are orthonormal. What is it called? These are called unitary transformations, if you know, which corresponds to rotation. Sigma is a diagonal matrix, like it is like almost think about what the identity matrix will do, nothing. What will it do if the identity that ones are changed by some scalars? It will exactly scale by that much on that columns, right? So the second part, the sigma part only scales the x-axis by sigma 1, the second axis by sigma 2, third axis by sigma 3 and so on. It's just a very simple scaling to visualize. If you start with a sphere, you will get an ellipsoid. In fact, and the major axis, minor axis, everything will be the original coordinate axis. The third part is U, which again is an orthogonal matrix or a unitary matrix. Hence, it's a rotation again. So, rotate, scale, rotate. That's what singular value decomposition says. And it tells you that you can do it with every rectangular matrix. So, in some sense, it is much more general than some of you who would have done a complete course on linear algebra would have seen eigenvalue decomposition and what is known as a spectral decomposition. So that works only for square matrices and most of the time only with diagonalizable square matrices and so on. In that sense, singular value decomposition is more general. Okay. By the way, how many of you have heard about Gilbert Strang? So if not, his linear algebra lectures are really popular MIT open courseware. His books are also very good. By the way, he finished teaching just a month ago. His last lecture was live streamed. It was a big event, right? So, and how many of you have heard about this podcast by Lex Friedman? So this is an amazing guy. I don't know, he almost finds the best people in every domain and does an interview. So there is an interview of Gilbert Strang by Lex Friedman, and I just watched it yesterday while, in fact I got it when I was searching the internet for SVD. The interviewer, Lex Friedman, asks Gilbert Strang, which is your favorite result in linear algebra, and he says singular value decomposition. Okay, so he says like it's a shame that most linear algebra courses stop with the eigenvalues, eigenvectors, and doesn't get into singular vectors. Yes, eigenvalues have its own reasons to be there. By the way, the singular values of A happens to be, or singular vectors of A happen to be eigenvectors of the symmetric matrix A transpose A. Actually, once we have reached there, it's not too much difficult to prove, but there is a very strong connection between eigenvectors and singular vectors, but singular vectors are much more general. Okay, so yeah, before winding up, I just want to hint at a few applications, some of which I have already done. This is only a very small list. Okay, I just picked a few things which are closer to like a data science kind of a application. The most common way you see SVD used is in what is known as principal component analysis. Given any data, you would want to know which is the most important low dimensional representation of that. It is almost SVD, just that you have to center the data before SVD. Okay, the literature on principal component analysis may not tell you this in this way, because it will talk about energy minimization, which direction you have maximum energy, and so on. That is because the centroid that you subtract is the bias or the mean, and what remains is the variance. Once you subtract out the centroid, what remains is variance, because we are also squaring and adding stuff. So the principal component, or the top singular vector of the centered data. Okay, so this is where you don't have to worry about thinking about Milky Way, but the sender being in another galaxy. Okay, in principal component analysis, if you are analyzing Milky Way, the sender will always be inside Sagittarius A. Okay, so you center the data, and then the top singular vector will tell you which direction has the maximum variation in the data, and variation is the information. Okay, which direction has the maximum variation in the data. The top two singular vectors of the sender data will tell you which plane has the maximum information. So in any compression algorithm, for example, image processing, you can do it this way, but all kinds of compression, if you want to compress the data, then you just take some top 10 or 20 singular vectors and project the data along that alone and store it. Okay, it will almost give you as without much loss. And how do you see whether 10 dimensions is the correct thing, 20 dimensions is the correct thing? That is where the singular values will help. Your singular values, you sigma 1 square plus sigma 2 squared plus sigma 3 squared will tell you how much of energy is already in the first 3 dimensions. You add the squares, sigma 1 squared, sigma 2 squared, all the way up to the d dimensions, you will get the total energy. So you can check what fraction of energy is there in the first k components, and if you are okay with capturing 95% of the energy, take as many dimensions till these things will come to 95, and it will actually happen very, very fast for any real data. Random data, nothing will happen, all the singular values will be kind of evenly spread out, but for images, any real data, this is going to be the key. Before this advent of deep learning and all, where you can handle, nowadays you can handle very large dimensions directly. Before that, the biggest research used to be on identifying a small set of features for the data, so that now this 12 features, 20 features used to be what you will feed to the neural network. Okay, that days have almost gone, but that days gave you a bit more of understanding of the data, and which are the good features were usually designed by the experts from the domain. Speech community had its own feature vectors like cepstral coefficients and all, which I know none of the data science engineers these days would have heard. It's like the log frequency and all. It's very connected to how we perceive music, spectrum and all. So lot of domain research used to go in designing what features best captured the data. But let's say you did not have the time to do a domain expert analysis. You still wanted to have a low dimensional representation. Principal component analysis was the go-to method. Okay, so at the heart of it is just SVD. Precisely, it is SVD of the centered data. Okay. Now the second one, all this, low rank approximation to matrices, how does Netflix tell you which movies you would like, all this matrix completion, that uses a low rank completion of a matrix. They use SVD in a slightly indirect way. Where we use SVD most directly is the following problem. Okay. So you all know what is the rank of a matrix, right? What is the rank of a matrix? Yeah, maximum number of linear independent columns in the matrix. It is same as maximum number of linear independent rows in the matrix. Proving that is a nightmare. It's not easy. Think about, it's a strange thing. You write some numbers in a rectangular fashion, and it turns out that no matter what numbers you write, the number of linearly independent columns is equal to the number of linearly independent rows. Okay, it's an amazingly strange thing. It's my most favorite result in linear algebra. Okay. So that's the rank. Alternate definitions are also there, like the largest cofactor, whose determinant doesn't vanish. Now, suppose your data matrix, because of noise and all, usually will have a very high rank. But for some applications, you may want to find which is a low rank matrix, like a rank 10 matrix, which best approximates the given matrix. Again, best approximation is quantified very easily. You take the term by term difference, component by component difference between all the entries, square it up and add. That is the error count. This is called the Frobenius norm. If you take the square root of it, it's called the Frobenius norm, but it's just the sum of square differences. You want to find A is your given matrix. You find a matrix B which is of rank small, rank 10, which as closely as possible approximates A. And the solution is what is written here. You do the singular value decomposition of A. So you will get V1, V2, V3 up to Vd, the right singular vectors, U1, U2, etc. up to Ud, the left singular vectors, and the value sigma 1 to sigma d. So if you want the best 10 rank approximation, what you do is from V, you pick just the first 10 singular vectors. Remember, they are still hierarchically ordered. V1 is the best singular vector. Next, so you take the first 10 and that will be your V matrix. Your V transpose will be its transpose alone, right? Similarly, on the U side, you just take again, once you have a numbering on V side, the numbering on U side will follow. Take just U1 to U10, and from the diagonal matrix, just take sigma 1 to sigma 10 and form a 10 by 10 diagonal matrix and multiply them together like this. The truncated U times the truncated sigma times the truncated V transpose. This is provably very easy to prove, like 10 minutes you will be able to prove it. This is the best rank 10 matrix which will approximate the data. And this also has started playing havoc in the area of data analysis. You really have started seeing so many applications which do this low rank approximation. Okay. This SVD also was used in an algorithm called HITS, which was probably the second best algorithm to PageRank. Okay, PageRank is not PageRank is what nowadays Google uses and almost all the search engine uses. That's slightly different. That doesn't use SVD directly, though there are spectral ideas embedded there. There was an algorithm before that called HITS algorithm, which used to model web pages as there are two types of web pages called authorities and hubs. Authorities are authoritative informations about authority in terms of information. Hubs are these link farms. If you go to a hub, you will get a link to a lot of web pages. This was an imaginary classification. In order to run the algorithm, you really need to know whether a page is an authority or a hub. You just have to imagine that there is something called a hub score of a page and an authority score of a page. How much of an authority it is its authority score. How much of a hub it is its hub score, and then you write it as this U and V matrix, and then the adjacency matrix of the directed graph of the web. That forms this A matrix, and then you find this left and right singular values. The top right singular value will give the authority score, and so on. So you use a convergence idea. This was used to rank web pages because before PageRank kind of completely took it over. Okay, yeah. So now references. Try to start with the Wikipedia article on SVD, but keep in mind that it's such an old technique that you will see different paragraphs kind of viewing it like the blind people seeing the elephant. but try to still read them. You will get a flavor of how rich an area it's. It's like this old wine. It only gets better and better because. By the way, how many of you have heard about this article by Eugene Wigner, called "The Unreasonable Effectiveness of Mathematics"? Okay, so what essentially he says is that everybody says it's so surprising that many natural phenomena can be modeled using mathematics, and mathematics gives you precise answers, predictions, etc. He says that's a reasonable thing to expect because you are modeling a phenomenon in mathematics. You solve it. The answer is supposed to match. What he calls as an unreasonable effectiveness is that a technique that you develop in one area without any effort, almost as it is, starts being meaningful in an entirely different area. This is a classic example. SVD was thought out as a way to think about linear operators, but suddenly in a data matrix it started giving best approximations and so on. So, very classic case of something which was invented for some other purpose suddenly being extremely useful here. Yeah, and the second one is the book that I am following, chapter 3. It's a fantastic book, Foundations of Data Science, again freely available online. It's still in a draft version. I don't think you can buy the printed copy. Ravikandan also has given some 14-15 lectures based on that book. It's available in YouTube. If you want a more polished animated lectures on SVD alone, I found this Steve Brunton's video lectures very good. He also has a companion book called Data Driven Science and Engineering. Okay, so I think that's all I had to say today.